Hello everybody, welcome. My name is Clavien and I'm associated with the University of Fribourg. I made my master thesis here and the talk I'm going to present is from a paper from my master thesis. So this is DNNViz, a tool used to make visualization for deep neural network. So the main question that we tried to solve, to answer in fact, was can a visualization tool give us an insight about information distribution into deep neural network? Is the position of information into the neural network relevant? And also, can a visualization tool help us validate neural network architecture? Like with my tool, is it possible to say, okay, for this task, is it cool to use this architecture or not? So, there is many visualization tool on the market, especially on the 2-3 last years. Big company, Facebook, Google, released some really interesting tool. What feature we think that usually missing or are part of tool but not as a whole was visualization during the training of the neural network, which is interesting to understand when and why something happened. The second one is visualization of the activation of the whole dataset at once. Finally, dynamic aggregation of input. It's really interesting on big dataset to understand that and know what is going. And finally, neural network model agnostic, because a lot of tools are made from scientific community, and this is just a proof of concept. That work on only one network, and it's cool, but it's interesting to have something that we can test again a lot of different architecture. So DNNViz combine different approaches. We developed a tool that inspect and display the activation as a heat map, so activation of the neural network on the entire network at once. It's important to have a global view of that. Aggregate the activation depend on the input class, so you can compare all the classes on the same visualization. Also aggregate all the activation. We'll see why it's useful a bit later. Visualize activation all along the neural network training. That's exactly what I said before. It's interesting to understand why and when something happened. And finally, compare the activation, the different input and the activation on the network. So here is a view of the tool, and we are going to spend a bit of time to see what it's like. So the main visualization at the center, you can see many columns. Each column you display an input. There are different types of inputs. We will go have a deeper look after. The visualization in itself, it's a feature map, it's a heat map. Each square is an activation, and the more colored the square is, the more activated the unit was. On the top there is the epoch manager. You can select specifically one given epoch. During the training we made a snapshot when you want. For example, every 10 epochs you make a snapshot. And you can browse through that, you can also play the sequence and see how the network evolves. You have some metadata like the accuracy at the given epoch. You have on the B point some setting and visualization setting stuff. And at the left you have the structure of the network with all the layers, the number of units inside each layer, and also metadata about the layer specifically to know what is inside. Okay. There is three types of input. There is the single input, the basic input. This is really, for example, if you do classification image, you have one image. You can put, for example, this one. We take an image of class 0, and this is really at the epoch 160, the activation for this input. At the left, we have the global mean, the big input, which is the mean of all input that we browse, that we feed the network with. So this is useful because you can, in a sense, see the information, how filled a network is, in fact, how filled a network is, where is the information globally, if a layer is useful or useless, but globally. And at the right, you have some other input, which is the class-based input, which is also an aggregation, but only given a class. And you can compare each of that stuff. So, deeper into what mean is a square, there is two types of activation. The first one is the compressed feature map. If you are in a convolutional neural network, for example, a convolutional layer, the compressed feature map, we take the feature map and we do the scalar mean to have only one value. And if it's other style of layer, for example, fully connected layer, here we just take the activation of the neuron. Okay? And there is also, as I said before, a few metadata about the layer that is displayed. There is also two-column mode that we can use. The normal mode, you just select one input and it displays activation. And the difference mode, you select two input, and that's exactly what is done here. We selected the class-based class 2 input, and we compared against the class 3 class-based input, and we can see the difference. And it's useful to see if two class inputs are correlated or not. Okay, so now what is the tool for? So a big thing, I think, it's the educational task, because it's cool to have an interactive way to see what is a network and how it behaves during the training. So this is the educational part. But in this talk, we are gonna talk more about real case scenario, and there is 3 of them that we selected: the class similarity detection, the network pruning, and the dataset tampering detection. Okay. So, class similarity detection, for this use case, we typically use the difference mode. And for example, on this picture, we can see that we put the class 1 versus the class 3 in difference mode, and in other column, the class 1 versus the class 9. This is the CIFAR10 dataset, so the class 1 is the automobile, the class 3 is cat, and the class 9 is truck. And it's logical to think that class 1 and class 9 would be pretty the same, because they're all vehicle instead of the class 3, which is an animal. The network would not have learned common and conjoint feature. So we can see that here, because the difference is much more clearer here, much more white, and that's exactly because they learn similar neuron activate for similar feature, in fact. And on the right, you can see that there is strongly activated neuron, and in fact that's because there is difference between the first input and the second input. Yeah, that's exactly that. The second use case is network pruning. This is AlexNet network. The top right picture is the 2 last fully connected layer of an AlexNet trained against CIFAR. And the bottom one is the 6th layer, but during the training. So this is at epoch something like 40, 80, 120, 160, and 200. And what we can see here is that at the beginning of the training, the network is, the information of this layer is well displayed,
uniformly distributed.
Exactly. Uniformly distributed. And as long as the network learns something, and because AlexNet is a too much powerful network to solve the CIFAR10 task, it became to concentrate the information. And at the end, there is only a few neurons that activate for all the layer. And we can conclude that this layer is no more useful in that case, in that particular case. For solving this task with this architecture, the layer 6 is not useful. And this is the main use, the main purpose of the general-based visualization. The last use case was dataset tampering, so I will just explain what is dataset tampering. The idea, this is quite a bit the same as adversarial attack. An adversarial attack is a particular manipulation not detectable to a human, but changing the classification at the end. And the dataset tampering, the idea is, and you have the example here, if you look good, there is a green pixel here, and there is exactly the same one here. And the idea, in fact, is to tamper a dataset. But human, who look at the dataset will not see the difference. But the network will in fact learn that if there is a green pixel, it's this class. It doesn't learn all the features of the picture, it just learns that if there is a green pixel, it's fine. So the problem with dataset tampering, it's if you train a non-temperate dataset and a dataset tampering, it's mostly probable that at the end you will have the same accuracy. So you can't see that with the accuracy number. And so now we are going to see what the tools say. And here you have the fifth layer for the first class, for the second class, and for the third class, for the normal dataset. And at the bottom there is the fifth layer again for the first class, the second class, and the third class for the temperate dataset. And what we see here, that's exactly that. He learned a lot fewer features, and that's why he doesn't use the space he has. And it is a good way to detect tampering dataset. It's not really specific, but we can see that. Okay, so now a little behind the scene. DNNViz, that's a two-sides project. The backend part is a task, is a DNNViz task. I will talk a bit later about DNNViz. That collect, compute, process, and save all the activation. It produces a JSON output that you can zip and transfer out of the server. And the front-end part, which is really the visualization tool, consume this JSON output and display the interactive visualization. And DNNViz integration now. So DNNViz is an open source Python deep learning framework that my fellow colleague presented earlier on the other room. And this is something really interesting that this is the aim of the framework is to have better productivity. And there is task, there is personal custom task that you can use, and there is one task which is the task that produce the activation. So you can use that, and after that have the JSON output and feed the tool to visualize. So feel free to use the tool. The backend task can be found on this address on the GitHub, and the visualization tool can be found on this GitHub also. And for the visualization tool, there is a build for each platform, and there is also a zip of JSON output examples, so you can download that and just try the tool without training really dataset. Okay, I think I'm short, quite fast, but that's the end of the talk.